Okay, let's get started today. So there's kind of two items on today's agenda. One is to get you acquainted with the fundamentals of the relational model so that you can understand the terminology we use when we start into using SQL databases. And the second is to get you a little bit familiarized with the databases that should have been created for you. So we'll kind of do a little bit with the relational model, then segue into having you log into your databases, and then we'll come back and finish up with some more information about the relational model. And then Tuesday, we'll really start talking about the query language associated with SQL. So the chapters 4 and 5 kind of give you the theory behind the relational model. And the way to think of it is that chapter 4 is really talking about what we would associate with the data description language. And chapter 5 is really talking about what we would call the data manipulation language. So in chapter 4, we're talking about how databases are structured in the relational model. So what constraints are placed on them. And then in chapter 5, we talk about the user view and how they are able to write queries. Now, we won't look at chapter 5 for probably a couple weeks, but that gives you a general idea of what's going on. And in our examples, we will use the branch and staff relations from the Dream Home case study. So that's the property management company we're talking about. And this actually shows you some of the initial terms that we will use with the relational model. So in the relational model, each entity is represented by a table. So in this case, we have two entities, branch and staff. And we call the tables relations. So the formal terminology for a table is relation. The more colloquial term is table. And each table has some number of columns, each column representing an attribute of that entity. So the branch has 4 attributes: the branch number, the street address, its city, and postal code. And we say that the number of attributes is the degree. So the branch has 4 degrees, and the staff relation has how many degrees? 8. So the degree equals the number of attributes. The cardinality is the number of rows that are in the table. And we refer to each row as a tuple. So that's the formal definition. And you'll also hear it referred to as a record. So each tuple, or each row, is describing one instance of that entity. So in the branch relation, each row represents a branch. In the staff relation, each row represents a staff member. Okay, so this just gives you the same information that I was just talking about. The one thing, the term at the bottom, a domain, is the set of allowable values for an attribute. It's like the declaration of a type for a variable in a programming language. So a table is actually very similar to a struct or class in C and C++, and the columns are very similar to the instance variables or the fields in a struct or class. And so the domain is simply the type of each of your columns. but again, you need to be able to sling the lingo, and in the terminology of the relational model, instead of talking about a type, we talk about a domain. And again, these are simply terms that I already told you about. The last one, a relational database, is a collection of normalized relations with distinct relation names. So by normalized, the key word here is, keywords are normalized and distinct relation names. And the meaning of the word normalized is right there. So the only shared information that we try to store in a relational database are what we call foreign keys. Now, going back to this slide, remember we talked last time about keys and how they uniquely identify an instance of an entity. So in this case, branch number and staff number are both keys for these two relations. And you'll notice that in the staff relation, there is a column called branch number. And that is the key for the branch relation. So we call branch number a foreign key. If you remember, it's essentially a pointer into a record or to a record in the branch relation. And if you also look at these two relations, it is the only redundant piece of information in the two relations. So all other attributes are unique. The only duplicated information is the branch number. And like I said, the branch number in the staff relation is essentially a pointer to a corresponding tuple in the branch relation. So again, normalized means that we try to organize our relations or our tables in a way that the only duplicated or shared columns are keys. Okay, and the domains that you can use in a database are a little more general than the ones that you've probably seen in C++ or Java or C. So you still have things like floating point numbers and integers and strings. But in databases, you also have things like dates that are important, times that are important. And so often you will have a domain type that is time, another domain type that is a date. You may have other domain types that you specifically create. So just like you can create your own types in C++ and Java using enumerated types, you can do the same thing in databases. So for example, you might say that a salary, rather than just being a floating point number, you might say that it's 7 digits in the range from 6,000 to 40,000. Okay, or you might say that a postal code is a character or a string with size 8, and those are postal codes in Britain. In the U.S., it would probably be either 9 characters or 5 characters, depending on whether you had the extra 4 digits at the end. And then here's the kind of alternative terminology that is used. So the formal terms are relation, tuple, and attribute. But users, and out in the real world, you're more likely to say table, row, and column. So those are the colloquial terms for them. And then if you're a file systems person, you're more likely to refer to a relation as a file, a tuple as a record, and an attribute as a field. In fact, that is probably the terms that you've used in courses like 302, 140, 360s. You had files, a line might be a record, and then each line would be delineated into fields. But in the relational model, we kind of rise above the physical implementation. We're more at the logical level. So we talk in terms of tables, rows, and columns. Okay, so before we get into all of this good stuff, what I want to do is take a step back and have you look at your databases. So if you have your laptops with you, what I'd like you to do is log into one of the Hydra machines. There are 30 of them. I believe this would also work on the Cetus machines. So I know how to do it on a Mac. I know some of you are unfamiliar. Actually, let me do this first. So the first thing before you can access, your database is you have to log in. Okay, on the Mac, you can just type a command SSH, which stands for Secure Shell, and then give it the name of one of the Hydra machines. There's Hydra 1, or even Hydra 0 possibly, to about Hydra 29. If you're on a Windows box, it really depends on what program you're using. There's PuTTY, there's different ones, so you have to figure out how to get to our departmental machines. So the Hydra machines, for those of you who don't know, are our departmental machines, and that's where our database server is. Now, should have all been sent the name of your database and a password for it. If not, please let Ryhan know. Okay? Yes?
Just a warning, do not put the password as a command line argument, because command line arguments are world readable through the /proc file system.
Yes. So you could put your password on the thing, but notice I'll go through the things here because my password is not on the command line here. But what's your name?
Demi, she, her pronouns.
Demi. Pardon?
She, her pronouns.
Okay. So, sorry, I lost my. So, at any rate, you should have the name of your database, which should be COSC 465, probably, fall 2016. I don't know if you're in 565. You might have 565 is your name, then underscore and your ID. Okay? If you don't, please contact Ryhan, and he should be able to create an account for you. So the command to invoke the SQL database is MySQL. Then you need to give it the name of the server, which is dbs.eecs.utk.edu, and you specify the server with the -h flag. The -p is telling it to prompt you for a password rather than providing it on the command line. So it will prompt, it's asking it to prompt me for a password, and then I will enter it in a moment. And I am telling it the name of the database that I want it to prompt me for. Then -u is promising it my username, which is B. Vander Z. So now when I hit return, it's prompting me for my database password. And as you can see, as I enter it, it is now let me in. And you should see something like this. It says, welcome to the MariaDB monitor. So we're actually not running an actual MySQL system. We're running one that is simulates one written by Maria. And the first thing I would suggest that you do is change your password from that random string that you were given to something that is more easily understood. And if you go to, I'll show it to you, but I also want to show you, if you miss it, the site. So on my web page, I have something called Getting Started with Your MySQL Database. And this is the command you'll want to execute. So you want to say set password equals. See, I don't want to do this myself because I'll just tell you what my password is. So replace new password with whatever you want your password to be. And thereafter, when you log in, you will use that password. And of course, please make a note of what password you chose. So I would do that now before doing anything else. The next thing I'd like you to do is to populate your database with a few sample relations that I created. So there's a script which you can get to by typing source and then /home, and don't put quotes around the file name. I'm just going to write it out. Actually, a second. Okay, so if you type that, or if you simply cut and paste from this page, either one works. It's probably safer if you cut and paste. But what that's doing is I've written a script at that particular location. If you hit return, it should create a number of relations for you. If you look at that script, which we'll take a longer look at later, but you'll see what it's doing is it's creating some tables. So it creates a student table that has 4 columns or attributes. A first name, that's a string of up to 10 characters. A last name, that's up to 15. A ID, that's 3 integers, and a GPA, that is a decimal, which is 3 digits total with 2 digits of precision. Then I create a table called courses, and that has 3 columns, a fixed width field of size 5, 2 variable length size fields of 30 and 20 with course name. Just a sec. Let me just get through this and I'll get through to your questions. And finally, a table called student courses. I'm betting that was, just a second. Yeah, I see what the deal is. Let me change that. Okay, now you should be able to do it. I bet that's what you all were. Now you should be able to load it. Yes? No?
You probably got a
Permissions error farther up.
yeah, SQL. Yeah, SQL.
Yes, there it is. Just a sec. Something happened over the summer that clobbered a lot of permissions, and then that's still not going to work.
It did work. It did work.
It did work? Okay, good. Okay. Okay, so you can see I created a third course then called Student Courses. One is student ID, course ID, grade, etc. And then I simply inserted a bunch of tuples into each of the courses. Okay, so you can look at that later, but it's just simply a quick instantiation of the database. And if you now look at your database, first of all, there is a command called show tables that will show you what tables are in here. And I've actually also previously loaded up some tables from the homework, but you see down here the three that were just created: courses, student, and student courses. If you forget what the columns are, you can say describe, and it will list information about each table. So you remember that one of the characteristics of a database management system is it provides a user catalog, which allows you to look up information about the structure of your database. So here we're able to get this is part of the catalog. We can look at information about each of our tables. And we'll get to what's the meanings of some of these other fields are. Right now, all you have to care about is field and type. Here's a very simple query that will let you look at the table. So select star. Star is a wildcard character saying list all columns from courses. So you can see that those are listed as a table with the various columns and the values of each row. And I could do that for my other two too. So select star from student courses, and it lists all the rows that I created for student courses. Okay. So that will basically get you set up so that on Tuesday we can get off into doing some of the queries, giving you some examples. Also, some of you, I think, want to get early starts on the homework who already know a little bit about SQL. So with this, you should be able to get off and running. Okay. Yes? How can you access the web page? Okay, the web page is, a second. The course website is web.eecs.utk.edu/BVZ CS465. So that will get you to the page that you see there. Then click on lecture notes. And then for next Tuesday's assigned readings, number 4 down here under assigned readings says getting started with your MySQL database. Okay? And that's got the information. Other questions? If you're having trouble with your database, either see me after class. I might be able to help, or it may be that you'll have to talk with someone on the IT staff. Usually I can help with simple things, but sometimes there's deeper issues. Okay, so hopefully you're now kind of comfortable with things. And that source command that I showed, by the way, if you use the arrow keys, you should be able to, it's like a history mechanism. It will allow you to go through your previous queries, which can be helpful if you've written a somewhat complicated query and you had a bug in it and you don't want to have to retype the entire thing. You can just use the arrow keys up and down to go through your history. You can use the left and right arrow keys to go to the right place, make a correction. So that's helpful. Yes?
Will it let you log in from multiple terminals, same databases, the same username and password?
I don't know. I haven't tried that. But I think the answer, I'm almost positive the answer is yes, because it's meant to handle multiple users at once. So I would say almost certainly. Yes?
The answer is yes.
The answer is yes. Okay.
How much table will
Pardon?
How much table will it have in our database?
The question was, how many tables will you have in the database? Not that many. By the end of the semester, no more than about 20.
Right now, because
Right now, you should have 3.
Okay.
Okay. The reason I have 7 is because I'd already loaded in some of the homework 1 tables. So I had another script. So the source command allows you to load in a file that consists of SQL commands, and that can often be helpful for doing a fast population of your database like I just did. Okay, and then to get out, exit. Gets you out cleanly. Yes? Yes, if you forget, so if you forget the, how do what? What, just wait, why do you want to get back to the command line? Okay, just a second. Let me go back in there. So you're saying if you leave off, okay. Okay, now you want to know how to get back to the command line? I think it's, let's see. It's not control that. Yeah, I mean the easiest thing to do in that case is to simply finish the command. Okay. I'll be honest. I'm not sure how to. I guess what I always do is just finish the command, and then if there's a problem, I go back. So I'm not exactly sure how to terminate the command without terminating your session. Okay. Any ideas? Nope.
Not that I can think of.
Okay. Okay. So generally, or just put a semicolon, and even if it's a bad command, it will terminate it and give you an error message, and then you can fix it. Okay, but
I think there's like /C, \C can do it.
that okay, give it. At any rate, that's my solution. Other questions? Okay, so headed back then to that was kind of to give you a bit of a break from some of this terminology, but we have to move back into terminology. So in the relational model, we talk about the definition of a relation as being a Cartesian product of some number of domains, where each domain represents a column. So for example, for a 2-column relation, we might say that column 1 has the domain of integers 2 and 4, and column 2 has the domain of integers 1, 3, and 5. And the Cartesian product of that domain gives us the kind of universe of pairs from which we may choose tuples. So hopefully you know from 311 that the possible universe, there's going to be 6 potential tuples, and you can choose any subset of those 6 tuples as a relation. Okay, so here I've shown the complete universe of possible tuples, but that doesn't say that that has to be the relation. That's simply the set of tuples from which you would choose to populate your database. Okay, so then of course you can specify, you could either manually list the tuples, which in practice is what we do. We simply manually list tuples, but again, we have to give you the mathematical foundation of a relation. So, from the mathematical sense, you could actually specify a relation as a set where you give some kind of mathematical criteria for selecting your tuples. So, in example A, I've said my relation consists of all tuples such that x is an element of domain 1, y is an element of domain 2, and the y value must equal 1. So in that case, our relation is 2 tuples, 2, 1, and 4, 1. So I'm drawing it from the domain where D1 is equal to 2, 4, and D2 is equal to 1, 3, 5. So in example A, I've said that any tuple that has the second value or the second column is 1 is a valid tuple. Therefore, you can take any value from the first domain and pair it with the 1 from domain 2. You get those two tuples. Then in example B, I've said that any tuple in the relation must satisfy the mathematical constraint x equal 2 times y. So there is only one such pair in the domains which will work, which is I can take 1 from domain 2 and 2 from domain 1. So take 1, put it in there, take 2, and you can see that that is a valid constraint or equality, but no other combination of values from the two domains will yield a similar satisfaction. So there's only one tuple in that particular relation. Okay, so mathematically you can specify what constraints the tuples must adhere to. Now, as I said, we do tend to manually list our tuples because in the real world they tend to be instances of entities. However, this does allow us to put integrity constraints on our tuples. So you can think of these as integrity constraints. So I might say something like if, let's say, x were salary, I might say, and x is less than 100,000. Okay, so that kind of would be setting a constraint on one of the domains. Okay, so we can keep building up. This would be a relation with 3 domains. And again, the Cartesian product you see there is the universe of all possible tuples. And then a valid relation would be any subset of these ordered triples. And finally, we generalize up to an arbitrary relation of size n attributes. And we take the cross product, and that is usually written using the notation you see there. So capital Pi is the, in this case, Cartesian product operator over all of the domains. So then you would choose your set of tuples from the set of n tuples that you've gotten from the Cartesian product. Okay, so that's kind of the mathematical definition of a relation. This last slide gives you the kind of general definition of a relation. So then we say that a relation schema is the name relation defined by a set of attribute and domain name pairs. So when I went and showed you this, I don't have it anymore. Just a moment. Okay, this is a relational schema because it's describing at least the first two columns are the relational schema for courses. So it's a named relation, which is courses, plus the set of attribute names and domain types. So in this case, the three attributes are course ID, course name, and location. And course ID is a fixed string of size 5. Course name is a variable string of size 30. Location is a variable string of size 20. So that is what we call a relational schema. And then the relational database schema is the set of all tables in your database, or the set of all relations in your database. I'm sorry, the set of relation schemas. So this relational database schema, in some sense, is your user catalog. So questions about that? Okay. So in the relational database, there are certain properties that hold. You can think of them as constraints. So the first makes sense. The relation name is distinct from all other relation names. So within the database, all relation names are unique. The second one is a huge restriction on relational databases, and it's one thing that has caused people to look to other database organizations as a way of representing data. So the second property says that each cell of a relation contains exactly one value. So for example, you cannot have a phone field that consists of 3 phone numbers. It can consist of only one phone number. Yes?
Could it have a string that contained 3 phone numbers separated by white space?
So the answer is yes, but then you're defeating the purpose of it. So the answer is it would pass the syntax test. Semantically, you have and run what it is supposed to do.
Okay.
Okay? So the answer is yes, as long as you said phone number and you said like varchar 100, and then you shoved 3 phone numbers in there, it would buy it. But you've now you've kind of subverted what it's supposed to do. Okay, so 1 atomic value or single value per cell. Each attribute has a distinct name. That makes sense. If you create a struct or a class in C++, you're not allowed to have duplicated field names, so the same holds for a relation. 4 is another big restriction. So the values of an attribute are all from the same domain. So for example, all zip codes might have to be, if I say that, all zip codes would have to say be integers. You couldn't have some be integers and some be strings. Or I'm a graphical user interfaces person, and we sometimes have buttons in graphical user interfaces that are bitmaps, and sometimes they are text. You can't do that in a relational database because they either have to be all strings or they have to be all bitmaps. So the values of an attribute are all from the same domain. You can't have, in effect, dynamic typing, which is a bit of a pain in the neck too, but so be it. Okay, another one, each tuple is distinct, so there are no duplicate tuples, no identical twins. Okay, what that means, if every tuple is distinct, what does that tell us about a key? What is one key always going to be? The set of all attributes in the relation. So if worse comes to worse, you can always create a key from all attributes in a relation because property 5 guarantees us that each tuple must be distinct. And 6, this may be hard for some of your mathematicians to get your heads around. The order of the attributes has no significance. So we can put the attributes in any order we want. So back here, when I said it doesn't, well, actually, this is fine. It doesn't matter in which order these three columns are listed. I could just as easily have listed them in the order location, course name, course ID. So the reason it doesn't matter is because the columns are named and the columns are unique. Therefore, I can put them in any order and there's no ambiguity as to what that column represents. Whereas in math, you don't tend to name your columns. Therefore, if you swap the columns, since you haven't named them, there would be ambiguity. So in math, the order of the columns matters, but in a relational database, the order of the columns does not matter because they are named. Okay, this was order of the attributes. So 6 is going across. Okay, 7 is coming down. So 6 was going across, 7 is coming down. So it's saying the order of the tuples has no significance, the order of the rows. I can put the rows in any order I want. Now, in practice, we do order the rows on some key because it makes satisfying the query more efficient if we enforce some ordering on the tuples. But that's a efficiency optimization. That's not a trait inherent to the relational model. So the relational model says that the order of tuples has no significance. Okay? So questions about that. Those are the properties of relations. Okay? There's also some terminology about keys. Okay, last time I talked about natural key and artificial key. Okay, here are some other terms you have to be familiar with. So there is this notion of a superkey. So it is any attribute or set of attributes that uniquely identifies a tuple within a relation. So here, branch number is a superkey because it uniquely identifies every branch. All four tuples are also, all four attributes are also a superkey because they uniquely identify it. There's an excellent chance that the last three attributes, street, city, and postcode, are a superkey. So a superkey is any set of attributes that uniquely identifies a tuple, and it could be a single attribute. Now, superkeys, as you can see, can be verbose. So what we're often looking for is a minimal set of attributes that forms a key. So back here, both branch number is a key, but so is branch number, street, city, and postcode. Well, we're looking for succinct keys, so we would like to find a minimum set of attributes that uniquely identify the tuples. So we would say that branch number is a candidate key because there is no proper subset that could uniquely identify it. Whereas we say that the superkey consisting of branch number, street, city, and postcode, we say that that is not a candidate key because a proper subset of it, namely branch number, is uniquely identifying it. Now, if I also claim that street, city, and postal code can uniquely identify a tuple, then that is also a candidate key. Those three attributes are. So I actually would have two candidate keys. One would be branch number, and one would be street, city, and postcode. Okay, and you might say, well, wait a minute. Branch number is smaller than the other one, right? It's got 1, the other one has 3. But nothing in candidate key says that there can be no candidate key smaller than it. It just says that no proper subset of that candidate key can be a key. So here, if no proper subset of street, city, and postcode can itself be a key, then those 3 attributes are a candidate key. Now, in general, from our candidate keys, we will choose a key that has the smallest number of attributes. So we choose branch number. But you should realize that every relation may have multiple candidate keys. So you'll see that property B, we call it irreducibility, because we cannot remove any attribute from that candidate key and still uniquely identify every tuple in the relation. So is that clear? Because this one always catches some people out every semester. You can have multiple candidate keys. Okay. So from the candidate keys, we typically choose one such key to uniquely identify. So we choose one of them as our primary key. So that becomes the first among equals. And as I said, typically the primary key is typically the candidate key with the fewest number of attributes. And typically it is an artificial key. Okay, not always, but typically it is an artificial key. And then we say that the alternate keys are the candidate keys that were not selected. So in this case, the combination of street, city, and postcode would be an alternate key for branch. Okay, and we've already gone over foreign key. A foreign key is a candidate key in a different relation. So we're basically using a foreign key as a pointer. So it is a candidate key in some other relation. So if we look here, branch number is a foreign key in the staff relation. Okay, so to give you some practice, here is a schema that we'll be using a lot of in this course as well, starting with homework 1. So this is a relational database consisting of 4 relations. A hotel relation, which lists all the hotels that we own. Then a room relation showing the type of room and the price for each room in each hotel. Then we have a set of bookings or reservations that tell us when guests are staying in our rooms. And finally, we have a guest relation that tells us the set of all guests that have stayed with us, maybe that are members of our guest program or honors program or something. Okay, so 4 relations. Actually, it would be more than just our honors program because we want all guests that have stayed with us. So if we look at this, you're going to see that it's easy to pick out primary keys in some of these relations. It should be clear that a hotel number should uniquely identify a hotel, and a guest number should uniquely identify a guest. However, it's not so clear what uniquely identifies a room in a booking. So for example, think about a room. Do you think a room number by itself is going to uniquely identify a room? And I see no. First, who's shaking your head? Why not? No, behind you. That's right. I could have many hotels, and each of them could have the same room number. Okay? Well, now I go on to hotel numbers. Hotel number going to work? No, unless every hotel of mine has only one room. Okay, so clearly that's not working. I really don't think that type or price is also going to uniquely do the trick. So in this case, we're going to have to look for some combination of attributes. Now clearly, I have told you that all 4 attributes will be a key, but we're looking for a candidate key. So what set of attributes do you think will give me a candidate key for room? Room number and hotel number together will give me a candidate key. Okay, I shouldn't have any duplicated room numbers within a hotel. That would be pretty bad, right? Then our guests will get confused. So presumably that is a candidate key. And it's unlikely that any other combination of attributes is going to give us a unique tuple. So you might say, okay, what about hotel number and price? But presumably there are multiple rooms within the same hotel at the same price. You would assume that there would be multiple rooms in the same hotel with the same type. You're probably not going to find any other candidate key. Okay, but booking is more interesting. Okay, booking's going to give us multiple candidate keys. Okay, so does anyone want to take a crack at what might be a candidate key for booking? Oh, by the way, let me give you some more information because that will be...
Everything but one of the dates, whichever one you choose to leave.
Okay, so I will make the thing. There can be no overlapping for a guest. The guest can't have overlapping bookings. Okay, we can't have a guest staying at 2 different hotels at the same time. So you can assume that we don't double book rooms and guests don't double book at 2 different hotels. Okay,
Oh,
so
that
that...
changes things.
Pardon?
That changes things.
Well, but you were in the ballpark.
Yeah, but you can.
Okay. Yes.
Guest number and either of the dates.
So guest number and either of the dates should work. Correct. Okay, so this is one candidate key. And then, just a second, guest number and date 2 should be a second candidate key because we said no overlapping reservations. Yes.
So do our hotel chain not allow things like conventions where you book like an entire floor under one name?
Yep, for the time being. I had to make certain assumptions for your homework, so that's what actually, I didn't make these assumptions. The book makes these assumptions. So, yes. So, I know what you're saying. Maybe not completely realistic, but the book was making some simplifying assumptions to make your life a little easier. So, yeah, not completely realistic, but we're not letting someone book an entire floor. So, we may be going out of business soon, but so be it. No weddings for us. Yes.
Could you add a hotel number to those? I mean, obviously you don't need it, but.
So you could, so I could certainly add hotel number to that. It makes it what we call a super key, but it's not a candidate key because it's not a minimal set anymore. Okay, so adding hotel number to it turns it into what we call a super key, but it's no longer a candidate key because it's not minimal. Okay, so usually we care mostly about candidate keys. Okay. But we're not done. We have other candidate keys. You may not stop with guest, so you got two of them, but there's more here. There are other candidate keys. Yes.
Hotel number.
I like
date
this. This is like a game
from,
show.
or
Hotel
date
number.
to,
Just
and
a
room number.
sec. I didn't get them. Hotel number.
Either of the dates.
Either of the dates. So we'll
and
take.
room number.
Very good.
And that works because, and that works even without the assumption that you can't book entire floors because a room cannot be booked more than once at a time. And
That's right.
Hotel, incidentally, a way to normalize it would be to have a globally unique
Booking
room
number.
ID,
Yes.
and that would become a foreign key in the room.
You are
That would
right.
become a primary key in the room.
Yes. But I chose not. The book chose not to do it because it's trying to mix artificial keys with other kinds of keys. So you're right. So hotel number, room number, date from, because we don't double book rooms. Or hotel number, room number, and date to would be both additional candidate keys. Okay? And that is probably going to do it. It's going to be either, the candidate keys are either going to be using the guest or using the hotel and room number. But there's 4 candidate keys for the booking relation. And we choose one of those to be the primary key. Yes.
Why would hotel number and guest number?
Okay, so the question is, why would hotel number and guest number not be? And the reason is you might make multiple bookings on different dates, right? So I went to Peru in May and we had 3 different reservations with the hotel for 3 different dates. So that's why that by itself is not enough. Yes.
For the foreign keys, does it have to be the whole set? Say, for instance, rooms, you have room number, hotel number, but hotel number is the primary key for hotel, so is that a foreign key there?
So yes, very good. So the question was, here with foreign keys, is hotel, I think if I'm not getting this right, correct me, but you're kind of asking what are the foreign keys here and does it have to be, so the foreign keys here are hotel number and guest number, and so hotel number for hotel, guest number for guest, and then there is actually a, right here, these two form the foreign key for room. So actually booking is got 3 foreign keys in it. And you'll notice that 2 of the foreign keys share a attribute, hotel number. So there's 3 foreign keys, 1 into hotel, 1 into room, 1 into guest. 2 of the foreign keys share a common attribute, and that's okay. Okay, but each of the foreign keys is a primary key of another relation, or a candidate key in another relation. Yes.
Are the names the only natural keys? Or can,
What do you mean? Oh, hotel name and guest name?
yeah, those are the only natural keys?
It depends on what you make your hotel name. If it's just Holiday Inn, it's not unique. If it's Holiday Inn West Knoxville and Holiday Inn East Knoxville, then it's unique. So I guess this is where you'd have to interview and find out, are the hotel names unique or not? But yes, probably, okay, in all probability, your hotel name is probably unique. I would say your guest name is unlikely to be unique. It's just too likely that there's going to be, in this big world, 2 guests with the same name. So you're probably not going to be able to say guest name is unique. Now, there's a good chance that guest name and guest address are a candidate key. Okay? Unless you get father and son living at the same address with the same name. But usually one is called Junior or something. So guest name and guest address might be, but remember last time how I said that's the problem with natural name, keys is they often come close to being unique, but you may get a couple that aren't, and that's why you introduce an artificial key. So my guess is that typically hotel name is probably unique, guest name is not, guest name and guest address together are iffy. So questions about this? Yes.
Yeah, when we were doing the candidate keys for booking,
Mm-hmm.
every candidate key that was generated had a primary key in it. Is that significant?
So had a primary key from another
Right.
relation in it. No, that's
Okay.
not. Although there is a good chance that, we'll get to it later, but there is a good chance that when you have primary keys from other relations in your relation and you don't have an artificial key, then there's a good chance your candidate key is going to come from some combination of primary keys from the other relations. That's a little too deep right now. We'll get to that in a few weeks. Good question. Yes or no? Nope. Okay. Other questions? Okay. Okay, we're almost done. So take a deep breath. So remember we said that last time when you do a data model, you come up with entities, and entities are modeled how in our relational model? How are entities modeled? Come on, if I had a matching question on an exam, they're modeled using a relation. So a relation and an entity have a one-to-one mapping. Okay? I also said that every entity has attributes. So attributes are modeled by attributes. Okay? Then there were relationships which I've kind of skimmed over, but just so you know, there are actually 3 entities in our hotel database. They are hotel, room, and guest. And technically, booking is what we call a relationship. So we say that a guest books a room in a hotel. So we actually tend to say that booking, while it is a relation, actually represents a relationship among the other 3 entities in our database. Again, we'll get to that more down the road. That's not something that's critical for you to know now. But a relation can represent either an entity or it can represent a relationship among entities. And booking actually is a relationship among entities. And finally, the 4th thing I said that you had associated with a data model were integrity constraints. So the relational model defines a set of integrity constraints. Okay, the first one is the notion of whether you can have null as a value for an attribute. So we all know about null pointers, okay? Point to nowhere. So null is a legitimate value in a relational database. It indicates that the value is either unknown or not applicable. So for example, let's say we had a viewing relation for our property management firm. So each time a client visits a property, the realtor fills out a viewing form to indicate that client viewed the property. Okay, well maybe the client leaves a comment like, I saw cockroaches in the sink, or the plaster was falling in the living room. So you'd leave a comment in the comment column, but other clients might not leave a comment. So in that case, we would put null. in that column to indicate that the value was, in this case, not applicable. Or maybe we forgot to ask the client, in which case it's currently unknown. So we say it deals with incomplete or exceptional data, represents the absence of a value, is not the same as 0 or spaces. So 0, if I have salary and it's null, that doesn't mean the salary is 0. That means the salary is unknown. Okay? It's a difference. Okay? And if you have a large number of nulls, then it may mean that the relation should be decomposed into subrelations so that that column is put off in a separate relation, but we'll talk more about that later. Okay. So going back to here, you now can understand the third column. So I was describing courses, and it was saying whether a null value was allowed for the field. So in all three cases, the answer was yes, a null value was allowed. Key, there would be a star if I had identified that field as a key, but it's not. And default values, the field defaults to no if I don't provide a default value for it. So that's the meaning of 3 more of those. Okay, so the second type of integrity constraint is something we call entity integrity. And what it means is that no primary key may be null. So we remember a primary key uniquely identifies a tuple. Therefore, having null, which is an unknown value, is terrifically unhelpful as a primary key value. So we simply outlaw it. Every primary key has to have a value. So if I went back and said that course ID, in reality, course ID would probably be a primary key, in which case that column would say null, that null is not a legitimate value. Yes?
If the primary key is just one column, is that still considered a tuple? Or is it tuple of 1? Or it's just...
It'd be rare to have a relation with only one column. Typically, a relation would have multiple columns. But that may not be the question you're asking.
And we've been working with smaller data sets, and
Okay.
usually it was just like one, like customer ID or something like that.
Okay, usually you would have something more associated with customer ID.
Okay.
So it'd be pretty uncommon to have a relation. I mean, there's plenty of relations that just have 2 columns, a primary key and a second attribute, but it's pretty uncommon to have just one. But you can ask me afterwards about it. Okay. Then the third thing is what we call referential integrity, which means that if a foreign key exists in a relation, then either it points to a valid instance of an entity in another relation, or all of its fields are null. One or the other. You can't have, so you know how a pointer can be a dangling pointer? Can't have dangling pointers in a relational database. So either the pointer is null, meaning all fields of the foreign key are null, or it points to a valid tuple in another relation. So you can't, let's say the foreign key has 3 fields, you can't have it where 2 of the 3 fields are null. They're either all null or none of them are null, and they point to a legitimate tuple in another relation. So that's called referential integrity. Okay, so these all kind of fit naturally with notions of pointers that you've already had. And then fourth, you can put general constraints on your relations, such as no staff member may have a salary that exceeds $100,000, or no realtor may manage more than 30 properties. Okay? And finally, remember we had this notion of views where we said we could construct different views for different users. So we talk about having a set of base relations where the data is stored. So in staff has columns for things like salary, date of birth, gender, things that we may want to be confidential and not viewable by everyone. But that would still be in the base relation. Then views are dynamically derived relations that are created from a query on one or more base relations. And you may also hear them referred to as derived relations or virtual relations. So as an example, I might say select course ID and location from courses. That's a view because that is derived from the courses relation but has only 2 of 3 attributes. So we call this a view. Okay? You haven't seen me do it, but there's ways to put together 2 relations. So let's say, well, let's go back to here. Okay, well, let's talk a bit more. So views don't necessarily exist in the database. They could be cached, and often are, but that's an optimization issue. So theoretically, they're re-executed every time that a view is created from a query, and the query theoretically is re-executed each time that the view is requested. So that's C, the contents of a view are defined as a query on one or more base relations. And they're dynamic, so if a change is made to the underlying base relation, then the view should be immediately updated. Okay, we've already talked about why we have views. And you could have a view from, as I said, multiple relations. So one view that I might want is the names of all people working at the branch at 22 Deer Street. So a view might be names of staff working at 22 Deer Road. Well, the only way to satisfy this query is for each staff member, you could go through it, but you have to look at their branch number to determine whether that branch matches 22 Deer Road or not. So that's a view that is over 2 relations. Now, the final view would consist of only 2 fields, first name and last name, and both attributes would be taken from the staff relation, but nonetheless, the view covers an operation over 2 relations. Okay, and we will leave updating views until next time. So we'll finish up with updating views on Tuesday, and then we're going to get into actual SQL queries on Tuesday.